Carbon buildup on spark plugs refers to the accumulation of black, sooty deposits on the plug's firing tip, typically the insulator nose and ground electrode. These deposits are composed mainly of unburned hydrocarbons and partially oxidized carbon compounds that form when combustion in the cylinder is incomplete. In appearance, carbon buildup is usually flat black or dull charcoal gray in color, dry and fluffy in texture like soot, or slightly oily if mixed with fuel or oil. The buildup tends to concentrate around the insulator tip and electrode. Chemically, it is composed primarily of elemental carbon, with traces of fuel additives, lubricants, and combustion byproducts, such as carbon monoxide and hydrocarbons. When combustion efficiency drops due to an incorrect air-fuel ratio, poor ignition, or oil intrusion, carbon doesn't fully oxidize to CO2 and instead accumulates as a solid deposit. Carbon fouling is multifactorial, and understanding each contributing condition is key to accurate diagnosis and long-term prevention. One of the most common causes is a rich air-fuel mixture, where there's too much fuel and not enough air. In such a case, combustion becomes oxygen-limited, and the extra fuel doesn't fully burn, leaving carbon residues behind. This can result from dirty or leaking fuel injectors, faulty mass airflow or oxygen sensors, a clogged air filter, incorrect fuel pressure regulation, or a malfunctioning engine coolant temperature sensor that causes the ECU to assume a cold condition and enrich the mixture unnecessarily. Another frequent contributor is short trip driving and cold operation. Engines that mostly run on short, low-speed trips rarely reach full operating temperature. During these cold starts, fuel enrichment via the choke or ECU cold map is prolonged, increasing the formation of carbon deposits. Weak ignition or misfire also plays a significant role. A spark that's too weak or erratic fails to ignite the mixture fully, leaving behind unburned fuel that turns to carbon. Potential causes include worn spark plug electrodes with widened gaps, aging ignition coils or plug wires, incorrect spark plug types or gap settings, or a faulty ignition control module. The wrong spark plug heat range can also lead to buildup. Plugs that are too cold, those designed for high-performance or turbo engines, don't reach the self-cleaning temperature of approximately 450 degrees Celsius. As a result, carbon can't burn off the insulator tip. Oil or fuel additive contamination is another factor. Excessive oil entering the combustion chamber through worn piston rings, valve guides, or PCV system issues contributes to sticky, carbon-rich deposits, while heavy fuel additives can leave metallic ash that blends with carbon fouling. Poor fuel quality, particularly low-grade fuels with high aromatic or detergent content, can increase residue formation if combustion isn't optimized. Lastly, incorrect ignition timing or sensor errors, such as retarded timing or malfunctioning crank sensors, can lead to incomplete combustion and lower exhaust gas temperatures, promoting carbon buildup. When spark plugs become fouled, they struggle to produce a consistent, high-voltage spark, creating a feedback loop of poor combustion, further fouling, and worsening performance. The typical symptoms include rough idle due to uneven firing from partial misfires, hard starting as carbon acts as a conductor when damp, allowing the spark to short to ground, loss of power or hesitation due to weak or intermittent ignition, poor fuel economy from incomplete combustion, and increased emissions with higher unburned hydrocarbons and carbon monoxide levels. The check engine light may also illuminate, commonly revealing OBD-II codes such as P00300, P0308 for misfires, and P0172 or P0175 for rich conditions. A spark plug serves as a window into the combustion chamber, and skilled technicians often diagnose engine conditions by examining plug appearance, a practice known as reading the plug. A normal plug shows a light tan or gray insulator with minimal deposits, indicating proper combustion and optimal performance. A carbon-fouled plug appears dry and sooty black, caused by a rich mixture, short trips, or weak spark, leading to misfires and poor fuel economy. Oil-fouled plugs show wet, oily deposits caused by worn rings or valve seals, often accompanied by blue exhaust smoke and misfire symptoms. Ash deposits present as light brown or white crusty buildup resulting from fuel or oil additives, and can cause mild pre-ignition. Overheated plugs show a white insulator, and blistered electrode caused by a lean mixture or advanced timing, potentially leading to detonation and engine damage. When inspecting plugs, it's important to check all of them. A single fouled plug usually indicates a localized issue such as a bad injector or oil ring, while fouling across all plugs suggests a system-wide problem like a rich mixture. Comparing cylinder to cylinder coloration helps identify imbalances in fueling or compression, and using magnification and proper lighting allows closer inspection for hidden cracks or glazing. Diagnostics for carbon buildup begin with an OBD-II scan to check for misfire or fuel trim codes such as P030X, P01-71 lean, or P01-72 rich. Freeze frame data can help identify the operating conditions when fouling occurred. Compression and leak down tests can uncover mechanical problems such as oil entry or poor combustion efficiency. Borescope inspections are valuable for visual confirmation of carbon buildup inside combustion chambers on valves and piston crowns. Checking spark plug resistance and gap ensures that the plug is operating within specification, as excessive resistance or incorrect gaps can weaken spark intensity. Finally, fuel pressure and injector flow tests confirm even fuel delivery, as leaking injectors can create localized rich conditions that cause carbon deposits on specific plugs. Addressing carbon buildup involves both immediate and long-term strategies. For mild carbon deposits, spark plugs can be cleaned using a non-metallic brush and a solvent such as carburetor cleaner or isopropyl alcohol. Heavier carbon deposits generally warrant plug replacement, as modern plugs often feature fragile precious metal electrodes, iridium or platinum, that can be damaged easily during aggressive cleaning. Sandblasting is not recommended because abrasive particles can embed in the insulator and cause pre-ignition. To prevent recurrence, it's essential to correct air fuel and ignition settings by checking for vacuum leaks, contaminated MAF sensors, or malfunctioning components. Updating ECU software may also be necessary if known calibration issues exist. Verifying ignition coil performance and ensuring correct plug gaps are equally important. Using the proper spark plug heat range, as specified by the manufacturer, helps maintain the correct self-cleaning temperature. Installing colder plugs should only be done when engine modifications justify it. Driving habits also play a significant role. Taking occasional longer drives that allow the engine to reach full operating temperature, often called an Italian tune-up, helps burn off minor deposits. Repeated short trips where the engine never fully warms up should be minimized. Regular fuel system maintenance is critical as well. Using high-quality gasoline or petrol with proper detergent additives, preferably top-tier certified fuels, helps prevent deposits. Periodic use of a fuel system cleaner designed for intake valves and injectors also helps maintain efficiency. Ensuring oil control by maintaining the crankcase ventilation (PCV) system and addressing oil leaks or excessive oil consumption promptly can prevent oil-based carbon fouling. Modern engines introduce new challenges in managing deposits. In gasoline direct injection (GDI) engines, fuel is injected directly into the cylinder rather than onto the intake valve. While this design improves efficiency, it removes the washing effect of fuel over valves and plug tips, increasing the potential for carbon buildup on plugs, valves, and piston crowns, especially during short-trip driving. Regular use of GDI-specific fuel system cleaners, periodic walnut shell blasting for severe valve deposits, and software updates that optimize injection timing and temperature can mitigate this issue. Turbocharged engines present a different challenge, as they operate hotter and often richer under boost. If tuning or plug heat range is mismatched, carbon deposits can form quickly. Using plugs specified for turbo operation, often one heat range colder and iridium-tipped for durability, is strongly recommended. Additionally, emissions and sensor systems such as O2, MAF, and EGR must be maintained properly, since faulty sensors can cause enrichment or lean spikes that contribute to deposit formation. Working around ignition systems requires strict safety practices. Always disconnect the battery before removing spark plugs to avoid accidental sparks. Applying dielectric grease to plug boots prevents corrosion and sticking. Proper torque application is crucial. Over-tightening can strip cylinder head threads, while under-tightening may cause plug blowout. Used spark plugs should be disposed of responsibly, as they contain metals and ceramic materials that should be recycled through auto parts stores or authorized recycling centers. In summary, carbon buildup is the byproduct of incomplete combustion and can result from fuel, ignition, or mechanical problems, or simply from driving habits. Consistent maintenance, proper spark plug selection, and correct combustion tuning are essential to prevention. Key maintenance practices include using OEM-recommended spark plugs in the correct heat range, inspecting plugs every 30,000 to 50,000 miles, or as specified by the manufacturer, keeping fuel and air filters clean, monitoring OBD-II codes regularly, using high-quality fuel and occasional cleaners, ensuring the engine reaches full operating temperature frequently, and replacing PCV valves or addressing oil leaks promptly. Ultimately, a spark plug may be small, but it serves as a frontline witness to what's happening inside your engine. Learning to read it not only prevents costly repairs, but also provides a direct line of communication with your engine's combustion health, one spark at a time.